Just a few reminders from lab today, for the 902 lab. We used this equation where big T is in seconds, big L is in centimeters, to determine the period T of a pendulum with length L. Okay, now this is the ideal, very close to the ideal. It's like this is within a fraction of a percent, it's a fairly small fraction of a percent of the ideal value, the 0.2. That probably doesn't correlate real well, or at least not all that well, to a handheld pendulum. So we're using this as an approximation. We timed ball rolling down a ramp. We wanted to look at how the slope of the ramp determines the acceleration on the ramp and use the associated equation of motion to answer a few questions. And the main goal here was to find our accelerations as accurately as possible. Now before I get into that, one thing I did mention, and it goes with this little picture here, the edge of the domino is slightly rounded so that the ramp as it rests on the domino is going to not rest quite as high as it would if the domino had a sharp edge. It's actually going to be tangent to this curve here at the edge, meaning that it's going to be very likely lower than the top of the domino. Okay, and you can kind of intuitively see why that is. It's going to rest a little further back on the domino, and that itself is going to, a little further back than where the edge would be, that itself is going to extend the run of the ramp a little bit more than what you would measure. And it's going to lie a little below the top of the ramp, which also tends to have its effect on the slope. So you can think about those two effects. Now that's going to be a very minor effect. I think it's going to be pretty minimal, but we have to kind of keep it in mind, at least we want to keep it in mind, as a possible source of error. Okay, well, having timed the ball down the ramp using either the synchronized pendulum, in which case you would have used this to help determine how long it took the ball to get down that ramp, excuse me, or the phone timer, and we did it both ways. Both timing methods, each timing method, the pendulum, the phone, has its own set of potential glitches, okay? Its own sources of uncertainty. And those sources of uncertainty, of course, are related to the way each individual uses that device, okay? And there are inherent, unavoidable, systematic errors that come about from the way each person uses and perceives the device that they're timing. Now we could improve the timing using electronic means and so forth, but we wouldn't get to do all the thinking that we're going to do here about sources of uncertainty. So you want to kind of keep that in mind. And we want to kind of analyze that. Once we see what all the data are, we want to explore where some of the apparent inconsistencies come from, because there will be apparent inconsistencies. Now I say apparent because if those inconsistencies can be explained by the uncertainties that naturally and unavoidably emerge in this situation, then we can't really say that our results are inconsistent. So it's going to be kind of interesting. Okay, how do we find the acceleration? Well, you could use a formula, but I don't want you to do that. I want you to think about what acceleration means. I want you to think about what velocity means. I want you to think about how the ball is moving down the ramp. So we want to base our analysis of acceleration on the velocity versus time graph for the ball. Now what do we know about the velocity versus time graph? We know that the velocity is 0 at what we're going to regard as the initial time, assuming that the initial time is the time when a ball is released. If the ball is released from rest, obviously its velocity at that instant is 0. So if t equals 0 at the instant of release, our graph is going to look like this. Now we're assuming that the graph is a straight line. Okay? That could be that the graph really isn't a straight line, and that's a source of error in our model. We're going to have to explore that. Okay. Well, as we did in class, and review the notes from class because I'm not going to go over it here. This is kind of a picture of how we do this, and people pretty much did mostly real well with this, but some people made errors, and the biggest thing I'll say is you have to always have an adjective on velocity. Okay, now this is a graph of instantaneous velocity. So if velocity has no adjective or no subscript or no other indication, we're talking about an instantaneous velocity. And this graph would show instantaneous velocity versus the clock time t. There's also initial velocity and final velocity. Initial velocity would be the velocity at the initial instant during a time interval. If this is the end of the time interval, the final velocity is the velocity at this instant. It would correspond to velocity that's here on the graph. There's an average velocity, there's a change in velocity. Okay? So you have to have an adjective anytime you use velocity. Even if you're talking about instantaneous velocity, I recommend that you use the word instantaneous until you really get good at distinguishing. So velocity always has an adjective. Average velocity could be indicated by V sub AVE, V with a bar over it. Initial velocity, V sub I or V sub 0. Use V sub 0. Final velocity, V sub F. So again, be careful about that. You really want to avoid that confusion. So, having found the acceleration, I wanted you to find your equation of motion. And then use that equation to determine where the ball will be after 2.5 cycles of whatever pendulum you used. Also, when, and maybe you want to measure that in cycles, because then we can use the pendulum to test our prediction. When in cycles will the ball be halfway down the ramp? Now, our equation of motion, and not everybody, although most use this format, not everybody seemed to remember this, and that's a little bit of a concern. Make sure you know these kinematic equations, and you should also know where they come from, how they're derived, what they mean, how they're used. So, your x of t function, your position function, is x naught plus v naught xt plus 1/2 a sub x t squared. Okay, what's x naught? X naught is the position x at the time t equals 0. V sub 0x is the velocity at the 0 time. A sub x, of course, is the acceleration. Okay, now, as an example, and everything we've done so far involves an initial velocity that's 0, so we don't even have the v0xt term in our equation. But we have to know exactly how we're measuring our position x. Okay, so I say that in my case, the position x was 2.3 centimeters at the initial time, where x stands for the position of the center of the ball. You have to say what x means. That's what x means. And I note that x equals 0 at the higher end of the ramp, meaning that the center of the ball was at 2.3 centimeters at the t equals 0 instant. So this is my equation of motion if I observe, or if I infer an acceleration of 12 centimeters per second squared. Okay? Now, these two questions are pretty easy to answer. I don't think anybody had much trouble with them. This one, people were okay if they saw that the question was actually asking about velocity, so that you would need the velocity function. Okay, what's the velocity function? Velocity function is the derivative of your position function. Take the derivative of your position function, you get your velocity function. And then when that is half the maximum velocity, you have to also know what the maximum velocity is, and that's right here in your graph if you know where to look. Okay? Now, one word of caution. I saw a lot of places where people writing down numbers without units. I don't want to see that. It's for your sake, also for mine. If I'm looking at what you're doing and there are no units in the numbers, then I got to figure out what units you intend on those numbers and what those quantities mean. If you've got the units on the numbers, it's very helpful for me to see what it is. And remember, I'm taking the role of your supervisor in an engineering project. Your supervisor is not going to want to come around and have to make all kinds of inferences. Your supervisor is going to want to see it in an organized and easily understood fashion. Okay, of course, when you're working these things out for the first time, it's understood that you're not going to put it in the form that your supervisor would obviously see. But one thing, as your supervisor, playing the role of your supervisor, I want to see units on every quantity that has units, and I want to see complete documentation of how you're getting everything. Okay, and I want it to be organized. I don't want the calculation of where the ball is interrupted in the middle by the calculation of the velocity when it's halfway or whatever. Okay? Don't want that. And then resuming again later. I want to be able to logically follow what you see. And again, that's for your benefit, both because you will be in a work situation where you really want to do that sort of thing. You have to understand what it takes to report to somebody, because you will be reporting to people, but also because it helps you organize your work in a way that makes it easier for you to keep track of where you are and what it is you're doing. Also reinforces what it is that you're doing in a way that helps you learn more quickly. Also gives you a really good reference for when you're reviewing, which you're probably going to need to do before tests and so forth. Okay? Okay, well, we have this. That's a different topic. I'll come back to it in a minute because it's kind of important, and it came up. One student was actually doing this, and that was very good. Okay. Now, at the end, and of course, go by the document. I'm embedding this video in the document. The thing we want to get for each of the two graphs is a graph of acceleration versus the actual ramp slope. Now remember, you measured the slope of the table using the level. You've got the slope of the ramp relative to the table from the height of the domino and its position under the ramp. But you don't, there's a difference. You got to compensate in a way that should be obvious to you for the ramp slope. Let me also say that slope is rise divided by run. I have people measuring that one end of the ramp is 0.8 centimeters higher than the other end on the table and saying the slope is 0.8 centimeters. That's not the slope. Okay, that's the rise. You've got to divide that by the run, the roughly 60 centimeter length of the ramp. So ramp slope means rise over run of the ramp. It's a unitless quantity. Make sure you don't make that mistake. And then think it through to see how you take the slope of the level that we used, the thing with the bubble in the middle of it, to determine the slope of the table and put those together to give me the actual ramp slope as measured from the horizontal being the direction, the plane that's perpendicular to the downward acceleration of gravity. Okay, here's your plane, here's your acceleration of gravity. Horizontal is perpendicular to that acceleration or to that force. Okay, the other thing here, student, if the acceleration is 16 centimeters per cycle squared, because you can certainly calculate your acceleration in centimeters per cycle squared instead of, you can measure your time in cycles. It doesn't have to be in seconds. So you could label this axis with cycles, and you're going to get a different slope for this ramp, which will give you a different acceleration, but it'll be in centimeters per cycle squared. Well, if you know how long a cycle is, and presumably you measured your pendulum, everybody did that, you can plug it into here and see how long a cycle would be if the pendulum really behaved in the ideal fashion. And then, knowing that a cycle takes 0.7 seconds, you can replace cycle with 0.7 seconds and get 16 centimeters over the square of 0.7 seconds. Work that out yourself. You see it comes out close to 32 centimeters per second squared. Okay, for the rest of it, read the instructions. Everything is linked.